And I wrote down that antiderivative for secant, which I doubt anyone in here knows off the top of their head. So the antiderivative for secant is the natural log of secant plus tangent. So let's talk about that, and let's talk about the other trig functions, antiderivatives, for all the antiderivatives other than sine and cosine. 8.3. So if you look back here at the 8.1 to this table of antiderivatives, notice that the three functions, actually I want to go four functions. If you look at tan and cotan, secant and cosecant, if you look at their antiderivatives, they're all logs. They are all logs. You see that? Every one of them integrates to a log. So, if they all integrate to a log, what form should you be able to write them in? Long form. Go figure. And it's very obvious for things like tangent and cotangent. We can write this as sine over cosine. It's not in log form yet. What's the derivative of cosine? Negative sine. So we're going to put a minus sign up there in the numerator. Now it's in log form. But if you put a minus sign up there in the numerator to offset it, you've got to put a minus sign out in front so that you're multiplying by 1. Now it's in log form, and so the antiderivative here is minus 1 times the natural log of the absolute value of cosine of x plus c. So there is our antiderivative for tangent. Now you could do a little finagling here if you would like. And sometimes when you look at these tables, you'll see the log property where they take the coefficient and fly it up into the exponent position. So if that -1 coefficient flies up into the exponent position inside the log, you'll get 1 over cosine, which is secant. So this is another form. Either one of these is totally fine. Doesn't matter. Both those are good. So that's if you pull the -1 up as an exponent, you move it up to that position. So you could write it that way. Cotangent, no hard work here at all because it's in log form already. We don't have to do any clever manipulation. Multiplying by 1 is clever. Very clever. So this is just natural log, absolute value, sine x plus c. So there is our, doesn't want to go to a square, rectangle. So far so good? So tan and cotan, pretty easy to find antiderivatives. Write them in terms of sine and cosine and put them in log form. Now the hard ones. So secant, we just saw it on the other slide. Its antiderivative is natural log of the absolute value of secant plus tangent. Now, we already said that you should be able to put it in log form. So this means that you need to be clever, multiply by 1. But we need to multiply by 1 in a way that actually is kind of clever. So here's how I remember what to multiply by. What is the derivative of secant?
Secant x tan x.
Secant times tangent, and so that's in my mind, secant times tangent, and I'm going to turn the times into a plus. And it turns out that that is the version of 1 that makes the integrand in log form. So I claim right now that the integral is now in log form. So if I distribute this secant in the numerator, we'll get secant squared plus secant tangent. And in the denominator, we have secant plus tangent. Do you see that that's log form? For it to be in log form, the denominator's derivative needs to be the numerator. And if we take the derivative of secant, bingo, right there, there's its derivative, sectan. And if we take the derivative of tan, its derivative is sec squared. Now it is in log form. Now it is in log form. So the last step, once it's in log form, antiderivative will be natural log, absolute value of the denominator. Uh-oh. Okay, it's still writing. That's good. Plus c. So there is our antiderivative. We are going to see this one a lot. You will get to the point where you don't need that step. So you don't need to put it. You're going to see it a lot. You can just write down the antiderivative.
How did you reason out the secants plus tangents?
Well, knowing that you're trying to put it in log form means you're trying to make it, when you multiply by 1, that you get log form. And if you already sort of have a little bit of insight, and that being this, like it's already sort of well known that it's natural log of secant plus tangent. So that kind of just gives us a clue that we want to multiply. If we know that the antiderivative is going to have a secant plus tangent in it, we're going to use secant plus tangent in the form of 1 that we're going to use. The question in my mind is always, okay, well, now that we know it works, the question is, how do you remember what to multiply by? And so that's where I think to myself, what's the derivative of secant? And then just separate it, turn it into a plus instead of a times. And that's a good way to remember it. But you will get to the point where you just write this down every single time because you're going to see it so much in a lot of the homework. Let's take a look at cosecant. Cosecant's a little more complicated. So we do need to multiply by 1. And what is the derivative of cosecant? Negative cosecant cotangent. And so you can do a similar thing. I'm going to use the cosecant and the cotangent for sure, but I'm just going to put a plus. You could do a minus and a minus. Minus cosecant, minus cotangent. That will work. If you just write it as plus, and you're going to see this one a heck of a lot less. So you don't need to get too obsessed with this one. But I'm going to write it like that, and then do what we normally do with the minuses. Then fiddle with the minuses. So let's first do this. So now the numerator becomes cosecant squared of x plus cosecant cotangent of x, all divided by cosecant plus cotangent. So let's just look at that for a minute and ask ourselves about the derivatives. So derivative of cosecant is minus cosecant cotangent. So we definitely are going to multiply the numerator by -1, which means we're going to put a negative on the outside to offset that. So now the derivative of cosecant minus cosecant cotangent, so that's good. And then the derivative of cotan is minus cosecant squared. So you could certainly put over here in the beginning, the derivative of cosecant is minus cosecant cotangent, so you could put a minus here and here, which means you'd have to put it here and here. Then you'd have to factor out the minus from the bottom. I find it easier just to not put a minus in there and then come over here, put one out front and one in the top. Doesn't really matter. And then we have minus natural log, absolute value, cosecant plus cotangent. antiderivative? The antiderivative. That did not work out.
That was weird.
Undo, 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 undo. All right, any questions on putting those in log form? Yeah, all right.
Can you transfer the negative into the log?
Yes, absolutely. So you could fly this up as an exponent, and then you would take the reciprocal of this quantity. It's not going to be that beneficial, though, because these denominators aren't going to match. So when you flip it over, you're not going to get anything that sort of reduces in a nice, neat way. Like if both of these had the same denominator. Oh, I guess they do have the same denominator, don't they? Oh, let's find out. Great question. Let's go. Let's look. Let's look. So in my mind, I was thinking that they usually don't do it because the denominators don't match, but now that you mention it, it looks like the denominators do match. So let's do it. So we would do that. And then in here, when we add these together, that reciprocal right there is going to flip it over, so we're going to get sine over 1 plus cosine. You don't usually see it written that way, but you could. You could write it that way. Yeah, that's a good point. And so when you end up with, when you look at this one, this one is going to be natural log of secant plus tangent. It's pretty easy to start to remember that, again, because the derivative of secant is secant times tangent. Here, if you can remember that it turns to be positive on the inside, but you have to put a minus on the outside. You can get to the point where you memorize both. That's the most important one to memorize, though, just because you see it so much. All right, so let's go ahead and do, this is a classic integration by parts. Now we've seen that integration by parts, it's sort of, let me take that back. No, I'll say it. So integration by parts is usually for a product. We've seen that we can use integration by parts for inverse trig functions and for the log function. This one we can think of as a product, and this is kind of a classic where we break off a secant squared and do that. And then we're going to treat this as the dv, and we're going to treat this as the u. Now we've already seen last class that if we go to these reduction formulas, if you did have the integral of secant cubed, if you know your reduction formula, you could use that. That's how we did it on Thursday of last week. But integration by parts works really nicely here because the integral of secant squared is tangent. So this part becomes tangent. And in the left column, we take the derivative. And the derivative of secant, again, secant times tangent. So let me come down a little lower. So du will be secant tangent times dx. So we'll have that. And then one thing we do when we have integration by parts with a twist is call the original integral something, because we're going to end up creating an algebraic equation. So the integral of secant cubed, I'll call it capital Omega. That's going to equal, and now we're going to do our integration by parts. So u times v, uv is sectan, uv minus the integral of v du, the bottom row. Bottom row is that product right there, so that's going to be secant of x times tangent squared of x dx. So that integral, we're going to have to use a technique for. Last week, we talked about the integral of secants and tangents. And recall that if the power on secant is even, we pull off a pair of secants and convert any leftovers. If the power on tangent is odd, we pull off a sectan and convert any leftover tangents. So secant, even, we have something to do. Tangent, odd, we have something to do. So we come over here, secant's not even, tangent's not odd. So both of those special cases don't apply. So we're in this third case. Right? The third case is if one of those first two don't work. So secant's not even, tangent's not odd, so we have to come down here. So it says we can convert the tangents with the Pythagorean identity. There's a few things that we could try. So the first thing that jumps out is that tangent is to an even power. Tangent squared, we know an identity for that. Right? So tan squared, and I'll just remind you, I drew a picture of this last week. That identity with tan and secant is that triangle there. That's the best visual you can have for that identity. It should become obvious. The tan squared is secant squared minus 1. Secant squared is tan squared plus 1. Right, from that Pythagorean, from that right triangle, you should see those identities pretty easily. So tan squared, we're going to have secant x tangent x minus, in here we're going to rewrite tangent as secant squared minus 1. So we have that. And then if we distribute that secant, notice what we get. So we're going to have sectan minus the integral of secant cubed minus secant. So we've got that. Oh, that's a secant cubed. Secant cubed. So let's distribute that minus sign and blow apart and create two integrals. We'll distribute the integral symbol. So when we distribute that integral symbol, we'll have minus integral of secant cubed of x dx. Minus a minus is plus the integral of secant of x. Well, we already have a symbol to represent the integral of c cubed, namely omega. Right? We said that that's what omega is going to equal. It's going to equal the integral of c cubed. And we already know the antiderivative for secant. The antiderivative for secant is natural log of secant plus tangent. Now, when this omega vanishes and goes to the other side, we need to have a c over here. We can put the c in right now because we have a c that got generated from this antiderivative here, so we can put it in and put it in now. And then we won't have to put it in again. It's already in. And then we're going to add omega to both sides. So the left side of this line above is 1 omega. We're going to move this omega to the left by adding omega to both sides. That's going to create a 2 omega on the left. And then we only have one step to go. And our last step is to What do we need to do to both sides now? Just divide by the 2, and then we've isolated omega, which means we've solved for omega, which means that we actually have the antiderivative for secant cubed without having done a crazy reduction formula thing. So let's see, plus 1/2 natural log secant plus tangent plus c. So there is our antiderivative. Directly, not using a reduction formula. Yeah, awesome.
Okay, for on the test, which one would you rather us use? This omega substitution thing or the power reduction?
Well, you're not going to, unless you're crazy, well, you're a little crazy. Unless you're crazy and going to memorize that reduction identity. Like, this is not something that I would ever ask you, no one would ask you to memorize that. So,
Okay, so you're not going to give those to us on the exam either?
if I wanted you to use the reduction identity, I would give it to you. Yeah, so don't memorize those. If I want you to use the reduction identity to use that method, if you see this one on an exam, you're going to do it with parts. Like it would say, use integration by parts. But it's kind of cool that you can do it by parts. Yeah?
So when we're using this omega substitution thing that we're doing, would we get knocked off once if we didn't say omega equals it, like just that? Do you want us to specify that's what omega is being?
You can break it. I mean, at some point you're going to have a multiple of omega on the left.
Yeah. So you want us to include omega on the left in the final answer?
Yeah.
Okay.
Yeah, you should.
Okay.
Because you're going to have, if you have 2 omega above, you have to have some omega here.
Yeah.
And when you do that division, this is now, like up here, if it's the same thing on the left, you don't have to write it every time.
Mm-hmm.
But here it's going to be different
Mm-hmm.
once you do that division by 2. So,
Okay. Thank you.
so I would have it at the end. All right, any other random questions with integration by parts? Before we go to our next integration technique, everyone's favorite. Not. So the next integration technique is probably one of the most important ones. It also seems to be the one that causes students the biggest headache because there's a lot of little nuances with it. Integration by parts is fairly straightforward. You've got a formula, uv minus integral of v du. And you really just have the question of how do I separate the integrand into a dv and a u? And usually there's only a couple of choices. So it's pretty limited in the places where you have to think hard. Trig sub, on the other hand, there's a lot of places where you have to think hard. So, trig sub, the goal of trigonometric substitution is to allow us to integrate basically 3 separate cases. It allows us to integrate things that are written in a sum of squares form or a difference of squares form. And we see this a lot with integrands, where we'll have, x squared plus 1 or 1 minus x, one of these forms. Possibly much more complicated. The u could be anything. It could be a function. It could be something much more complicated. The general idea, though, is that if we see a sum of squares or a difference of squares, we can do it. So I need a way to distinguish between these 2 difference of squares. I will refer to this as a difference of squares with a leading one, and this as a difference of squares with a trailing one. So that's how I'm going to distinguish between the 2. Right? They are both differences of squares. I'm going to focus on that one, though, and call that a diff of squares with a leading one. That, the difference of squares with a trailing one. Okay. And of course, the Pythagorean identities should be jumping out at you. You should be thinking about the Pythagorean identities, and here is what we're going to do with the Pythagorean identities. So these three forms that we're going to see right here are going to lead to three different trigonometric substitutions. And we are only going to use three. So with this first one, what we are thinking about doing is letting u be tangent squared. So the idea is that it's more beneficial in the long run, most of the time, if you can combine terms into a single term. A single term is generally preferable. You can take the square root of a single term, whereas you can't take the square root of u squared plus 1. But if somehow you can combine two terms and make them into one, it's usually more algebraically friendly. You can take the square root of a single term. You can, if you have a single term in the denominator, you can split fractions really easily. Like there's a lot of things you can do. So the idea here is that if you look at the Pythagorean identities, we look at this one, we've taken two terms, a sum of squares, and turned it into a single square here. Down here, I'm going to take these two trig identities and rewrite them. And I'm rewriting them in a way so that here I have a difference of squares with a leading 1. So the idea is that, well, if we have something like this, we could let u be sine of x right there. And then we'd have, this fits the 1 minus u squared form. And then down here we have a difference of squares with a trailing 1. And so u and secant are playing nicely together there. Okay, so these two identities, sine squared plus cosine squared is 1, tan squared plus 1 equals secant squared, those are the two that we are going to use for all trigonometric substitution. We only have three choices, traditionally. You could use the other three trig functions if you wanted to. There's no reason to. With trig sub, it's always going to be sine, secant, or tangent. Sine, secant, or tangent will always work. No need to think about cosine or cosecant or cotangent. So we're using the three non-co-functions, sine, secant, and tangent. None of the cos. No cosecant, no cotangent, no cosine. Just the three non-cos. Those are the only three we need. The next thing we are going to need in order to make this all work are the basic inverse trig function integrals. Sine square, the integral of this, 1 over 1 minus x squared, all square rooted. That's inverse sine. So you need to know your three basic inverse trig integrals. Now, we have to be a little careful with this inverse secant one. You will see sometimes that the derivative of inverse secant will have an absolute value around that x. And it depends, we're not going to get into the nitty-gritty of why that is, but you will see this frequently, and it has to do with the definition that the book is using for inverse secant. All the inverse trig functions are based on restricted trig functions. When you look at inverse sine, it's based on a restricted sine. Inverse cosine is based on a restricted cosine. Inverse secant is based on a restricted secant. Different books will restrict secant differently, which is a total pain in the neck. It'd be nice if they all did it the same way. So sometimes you're going to see that absolute value, sometimes you're not, based on how they decided to define inverse secant, how they defined the restricted secant. Not really going to come into play in Calc 2. All right, so it's not really a headache you have to worry about. So you can either think about those on there or think of them not. Another thing they'll do in this book often is just x will always be an angle that works. It's always going to be something that's going to work. And x is always going to be a number so that this integral is going to work. You don't have to worry about the absolute value. We'll talk about it when it does matter. Dan, question?
That's not in the printed notes, but
This-
there's each remember.
Oh, that is not?
Yeah, it's not. So
Oh, okay, yeah. It might be on the next page.
so the next page is just.
Oh, no, okay, good, yeah, yeah. Will you send me an email to remind me?
Yeah, of course.
Okay, so make sure you have these basic inverses down, because what we are going to do is use these basic inverses, and notice that the basic inverses for the inverse trig functions have a 1. When you go back and look at this table up here, right, they do the 1/a stuff. Like there's in all of the inverse trig functions, they've got this x over a, it's a squared, not a 1. There's an x over a 1 over a, an x over a 1 over a. And you have to trust me on this. It's going to be easier to do trigonometric substitution if you just know your basics. If you want to deal with the a's, you can. It's more complicated though. You have to remember more identities, and you have to remember which one has an A and which one doesn't, which it's not that hard, but it'll be a lot easier in the long run to do trigonometric substitution if you just use the basic 3 and then a little bit of algebra. So here is how we're going to do this. So, and the textbook is not going to do this basic piece of algebra first. Using the algebra is going to make it easier in the long run, and it's a very good skill to hone your algebra a little bit better than it might be. So the first step that I will always do with any of these that are going to use trig sub, so remember that we talked about the sum and the differences of squares either had a leading one or a trailing one. I want to have a 1 in here. And so here's how that's going to work. In order to force there to be a 1 instead of a 4, I'm just going to factor out the 4. So the 4 is going to come out. It's in the denominator. It's coming through a square root. So when you factor a 4 through a square root, what does it turn into? A 2. So that's going to be a 2 in the denominator. So we have this. And in this case, we have a definite integral. Okay, now when we factored out that 4, there was a 4 right here to factor out. But there's not a 4 in front of that x squared. So what do we do if there's no 4 and we need one? We make one. So yeah, we end up with a division, but if you need to, you can do this. Write that as 4 over 4 in front, right? We multiply by 1. We're clever. We know how to multiply by 1. And we multiply by the form of 1 that works. Now there's a 4 in front of both, so that 4 factors out as a 2. And now over here we're left with x squared divided by 4. Okay. Now our goal is to have a difference of squares in this denominator. And we're not quite there. We've got one more step before we have a difference of squares. So to make it a difference of squares, this step you're going to often just do in your head, or we're going to write this as x divided by 2 quantity squared. And that should sort of remind you of the 1 over a thing. A would be 2 in this case. Now we're in the inverse trig form where we have a difference of squares with a leading 1. So we have a difference of squares with a leading 1, and now we're ready to do trigonometric substitution. So that's our first step. We want to turn this quantity inside the root, that difference of squares, we want it to be a single term.
If it's not a perfect square, like say it was x squared over 3, would we write the numerator just square root 3?
Yeah.
Okay.
Yep. So if this was,
Or denominator.
yeah, this would end up, if this was a 3 here that we factored out, that would be a 3, and then this would be x over root 3.
Okay.
Yep. So now we have to ask ourselves sine, secant, or tangent. Those are the three choices. Only three. Sine, secant, or tangent, no cos. So we look right here and we say to ourselves, which one is an identity? 1 minus sine squared? That is an identity. 1 minus sine squared. Right? 1 minus sine squared is cosine squared. 1 minus tangent squared? Right? It's tan squared plus 1 is secant squared. And then the other one, secant, 1 minus secant squared is not an identity. 1 minus secant squared would be negative tangent squared. You can't take the square root of negative tangent squared. There's only one that's going to work. Difference of squares with a leading one, we're going to use sine, because 1 minus sine squared is cosine squared. So here's how we're going to do it. We're going to say, oh, let's let x divided by 2 be cosine of theta. Sine of theta. So now, when we, over here, that's 1 minus sine squared. 1 minus sine squared is cosine squared. Square root of cosine squared is cosine. So it completely unravels the square root of a difference in the denominator. It's all going to turn into a single term, which is always a good strategy. If we can get down to a single term, we're good. So we're going to do our differentiation step here. Now we're going to do our substitution in here. So we have the half. Often with trig sub, you don't want to deal with new limits. You can if you want, but usually I'll just put placeholders and go back to the original limits in the end. And not even think about inverse trig functions until the very end. So let's see. Numerator, x squared. So here is our equation that relates x and theta. If we multiply by 2, we see that x squared is 4 sine squared. So that's the numerator. Dx. Hopefully you're not one of those bad students that leaves off your dx anymore, because now it really matters. That dx has to get replaced with 2 cosine theta d theta. So we'll put that in the numerator. 2 cosine theta d theta. So now we've replaced the x squared, we've replaced the dx. Now the square root in the bottom, that becomes the square root of 1 minus sine squared. We'll do a little simplification. We're just going to use placeholder limits for now. We'll get back to them later. 4 came out, so we're left with sine squared cosine in the numerator. In the denominator, 1 minus cosine squared. 1 minus sine squared, cosine squared. So we have square root of cosine squared. And what's the square root of cosine squared?
Would it not be 2?
To where?
If we bring the 4 out to the front.
Oh, but we also have a 2 here. So we have a 4 and a 2. All those constants are out in front. You see it?
I missed the 2.
Yeah, that 2 is kind of hiding in the middle. Hiding in plain sight.
Like, I haven't gone insane yet, have I?
No, not yet. No, you're totally sane. You're totally sane. Regardless of what your sister says. Okay, so square root of cosine squared. Here is where we have to be a little careful, because we have talked about this this semester. What is the square root of x squared? That's not a square root symbol. That is not a square root symbol. I know that. Square root of x squared is absolute value of x. That is the square root of the square. Absolute value. Because that symbol, that root symbol, means the positive square root. So the positive square root of x squared is absolute x, because we don't know. X could be positive, x could be negative. Who knows? So technically here, we should get the absolute value of cosine. But on this little interval over here, they've chosen x's that are in quadrant 1, and in quadrant 1, cosine is positive. So we don't have to worry about it. So the square root of cosine squared is cosine. So that's going to cancel with this cosine in the numerator. So this gives us 4 integral with placeholder limits of sine squared of theta d theta. And how do we integrate sine squared? Power reduce. So power reduce, so a 2 is going to come to the front in the denominator. I won't simplify it yet, just so that it's a reminder. So we have that. And now we can integrate, so the 4 divided by 2 is a 2. The integral of 1 is theta. The integral of cosine is sine. Same angle. Reverse chain rule, divide by 2. And then we have our limits. Come on. Then we have our limits that are placeholder limits. That stage. All right, any questions to that moment? So we're going to distribute the 2. So we're going to get 2 theta minus sine of 2 theta. Okay. One step at a time. Now, we have information about sine of theta, no information about sine of 2 theta. So we need to use a trig identity here, which we'll use this trig identity a lot. Sine of 2 theta is 2 sine theta cosine theta. So sine of double angle for sine. Need more space. Okay, so just double angle. Now we get to draw a picture. So we need to turn these thetas over here back into x's. We need to back substitute. That substitution right there tells us everything we need to know. And here's what we're going to do. We are going to draw a triangle with theta. We'll always draw it like it's in quadrant 1. So draw it like it's in quadrant 1. And we label 2 of the sides of the triangle based on that substitution step. Sine of theta is x over 2. Well, if sine of theta is x over 2, then there we go. And then we're going to have one missing side, which we find by the Pythagorean identity. So we have that. Now we know sine, cosine, tangent of theta. So now we can come back over here, and we have 2 theta. If sine of theta is x over 2, what does that make theta? Isn't theta then just inverse sine of x over 2? Ooh, that's horrible. Inverse sine of x over 2? So that's down here. So this is going to be 2 inverse sine of x over 2. Let's see, like that. Minus 2 times sine theta cosine theta. So 2 times sine of theta is x over 2. You can look at your triangle. And then what is cosine of theta? So cosine of theta is the root over 2. So root of 4 minus x squared plus c. So there is the antiderivative. And then we have one simplification step. We can cancel out one of these 2's. Other than that, nothing else we can do.
We have one
Say again?
You have limits. It's on.
Oh, it's a definite integral. Thank you. We're not totally done yet. I mean, that is the antiderivative in general, for sure. But we still have more work. You're right. What were those original limits?
0 and the square root of 2.
0 and root 2. Okay, thank you. All right, so we found our antiderivative. Now let's evaluate our antiderivative. Notice that if we plug in 0, do you see that we get 0? Inverse sine of 0 is 0. Inverse sine of 0 is the angle on the right with the sine of 0. Plug in 0 there, we get 0. So 0's out. All we have to do is plug in the root 2. So we're going to have 2 inverse sine of root 2 over 2 minus, that's going to be a root 2 over 2 also. Root 2 over 2. Root 2 goes in there. We square it, we get 2. So we get a square root of 2. So there, we just have to simplify that. Yeah, definite integrals are a little more than indefinites. What is inverse sine of root 2 over 2? In radians? Pi over 4. So we're going to have 2 times pi over 4 minus 1. So we get pi divided by 2 minus 1. There is our definite integral. That is the trig sub process.
When we go from 4 times the integral of sine squared theta d theta, where do we get 4 over 2 from?
Because the identity, the power reduction identity says sine squared of theta is 1 minus cosine 2 theta over 2. So that over 2 is out in front.
And you said that's the
Power reduction?
power reduction. Okay.
Power reduction? Carter?
I don't understand the substituting. It seems strange. I didn't really follow it.
Let's see. So here is the other identity we used, sine of 2 theta. So substitution?
With the triangle.
Oh, with the triangle.
Yeah.
So do you see the green part?
Yeah.
So sine is x divided by 2, so we label the two sides that match the ratio that we used.
Okay.
Pythagorean theorem to find the missing side, c squared minus b squared,
Yeah.
square rooted. And then we plug that in. So right here, we're down to this trig function that's got a double angle no good. So we use that identity to get down to single angle. So now we have sine of theta, cosine of theta, and theta. Theta, we just solved this equation for theta, so we take the inverse sine of both sides. And then here, sine of theta is that over that. Cosine of theta is that over that. So we use opposite over, you see it? Opposite and adjacent over hypotenuse. Yeah, you're going to start to love it. Because that's going to end up being the easy part.
It's so cool that so many years of math go into that one problem.
Right? It uses everything. In Cal 2, we use all the trig identities, all the algebraic stuff.
It's a shame we didn't use a quadratic formula in this one as well.
I know. Maybe we could do that next. Courtesy.
That was probably the most sinister thing I've ever heard
We can
in
try.
math class.
What?
Good try.
Use the quadratic formula for everything?
No, also in here.
Oh, also.
I figured out a way.
Okay.
I figured out a way.
So here's another one. This one is an indefinite integral.
Thank goodness.
And we already did stuff like this earlier that were definite integrals. Like if we had something like a 0 to 6, we could do this geometrically. So we showed that we could do this geometrically with a definite integral if that definite integral was representing the area of part of a circle. Now we have an indefinite integral though, so we don't have that luxury of using geometry. So the only thing we can do is trig sub here. This is we looked at some of these even earlier this semester where we had a sum of squares or something or a difference of squares and we couldn't do it. Anytime you see a sum or difference of squares, now you have a technique. So step one is to put it in inverse trig form. By that I mean create a leading or a trailing 1. So let's factor out 6. Factor out the 36, which turns into a 6. And then this is going to be a 1 now. There is no 36 over here to factor out, so we're clever. So we know how to multiply by 1. We're going to put a 36 over 36. So we factored out that numerator 36. That created a 6 out in front. We still have a 36 here. We want to write it as a single square. So we're going to rewrite it like that. Now it's in inverse trig form. It's in trig sub form. We've got a leading 1. A difference of squares with a leading 1. So very similar to the last one, we are going with sign. Because 1 minus sine squared is an identity. 1 minus secant squared is not an identity. 1 minus tan squared is not an identity. So we're going to say, oh, let's let t divided by 6 equal sine of theta. Take the derivative of both sides. And if you're more comfortable multiplying, if you don't like division, you can move the 6 to the other side. Doesn't matter. You know how to do algebra. So then we take the derivative of both sides. We've got that. Now we have to do our substitution. And we end up with, again, 1 minus sine squared. And once again, 1 minus sine squared is an identity. So we have that. Yeah?
Instead of memorizing the identities, would the things always match the derivatives of the inverse?
Yes.
Okay.
Yeah. Yeah, if you have your derivatives down, you can use it that way. Square root of cosine squared. We are going to assume in this book, they're not that uptight about these things. You know, technically, this is only true if cosine is positive. Cosine's only positive in quadrant 1 and quadrant 4. You know, so there's a little bit, you just have to be, if there's an issue with domain, they're going to tell us, right? We'll just assume that we're in quadrant 1 and that this is the case. And then what's the integral of cosine? Negative sine plus c. Now in this case, oh, wait, negative or positive? Positive, thank you. Now in this case, we don't actually need to build the triangle because this one is simple enough that it's just got the sign in it. Let's build the triangle just in case though, so that you can see what we would get. So our triangle, we always build it like it's in quadrant 1. And that does not look like a triangle in quadrant 1. So we always want to do quadrant 1 type of triangle, where we think of theta down here, and sine is going to be t divided by 6. So the square root of 36 minus t squared is going to be the missing side. And again, we don't need it in this case, but we did it anyway. Sine of theta is t over 6. Something seems very wrong. Oh, crap. We did forget something. It's like, this seems way too easy.
We didn't substitute
The
d2.
d theta. Yeah, we forgot this part, or I forgot this part. D theta, what's d theta? That just seems way too easy. Trig sub never feels easy, so that's a clue that something's wrong. So here is d theta. So there is d theta. So this d theta has to get replaced with dt divided by what?
Wait, are we replacing dt or were we replacing d theta?
We're replacing dt, sorry. Because I wrote d theta there. That's where the mistake is, right there. Yeah, thank you. Good catch. Oh boy. So what does dt equal to?
6 cosine theta.
Yeah, 6 cosine theta. So right here, dt is 6 cosine theta d theta. Thank you. So we're replacing this dt with all of that. Everyone tracking that? So we're converting all the t's over to thetas. The t over 6 is sine of theta. dt, after we take our derivative, is 6 cosine theta d theta. So that dt is turning into 6 cosine theta d theta. So that is going to bring us out to 36 out in front. Now we have this. There we go. That looks less easy.
Then you have to power reduce again?
So, yep. So we're going to take the square root of cosine squared. We're going to assume that everything is cordial. So the square root of cosine squared is cosine. So that's going to give us 36 cosine squared integral. And then we have to power reduce it. Power reduction is going to be 1/2. So 36 divided by 2, the 1/2, and we'll pull it out in front. And this is going to be 1 plus cosine of 2 theta. So we're going to have 18 times the quantity theta plus sine of 2 theta divided by 2 plus c. Yeah. Okay, so sine of 2 theta, what's sine of 2 theta equal to? 2 sine theta cosine theta. So we're going to use our double angle identity. So this is all going to reduce to 18 theta. We distribute this 18. And then this is going to be a 2 sine theta cosine theta. Those 2's can cancel, so that 18 is actually going to stick around. And we're going to have 18 sine of theta cosine of theta plus c. This step right here, the original substitution allows us to solve for theta. Theta will be the inverse sine of t over 6. So theta is going to be replaced with that, inverse sine of t over 6, plus (18) multiplied by sine of theta. If we look at our triangle, sine is opposite over hypotenuse, so t divided by 6. Cosine, if we look at our triangle, cosine is adjacent over hypotenuse, so that's going to be square root divided by 6 plus c. And our final answer, and no matter how simple an integral looks, if you're going to use trig sub, it's going to be long. So I think we're going to end up with 1/2. Is that right? 1/2? Yeah, 18 over 36 1/2 times t times square root 36 minus t squared plus c.
Why is it a half?
18 divided by 36?
Oh.
Would it be okay if he just left the 1/2 under the?
Yeah, absolutely. You could write that as 2 over 2. Yep, definitely. Totally fine. Okay, so that is the trigonometric substitution process. Long. Yeah. You'll hate it even more in a couple days. Because they get harder.
What, are you gonna throw complex numbers in there or something?
No complex numbers. And to avoid complex numbers, we just, like right, if you think about the substitution we made, here we aren't going to have to do any worrying because 1 minus sine squared is always going to be positive no matter what. Cosine squared is always going to be positive no matter what. So it's going to work out, but you could get a headache with complex numbers if you had the square root of a negative in there somewhere. All right, ready for a break? Carter, you ready for a break? All right, let's take a break then. The next couple have a plus. And it's very easy to remember that if you have a plus, a sum of squares is always tangent. T looks like a plus. Tangent is always the trig sub for plus. Tangent, plus. The difference of squares are either sine or secant. So those are the ones that are a little more complicated. Tangent is the easy one. So if you have a sum of squares, you want a tangent. So now we have a sum of squares in the bottom. We have a 3/2 power, and you can do all sorts of weird combinations now. If it's just a square root, no problem. 3/2, no problem, whatever. So we are going to, and there's no issue with the leading coefficient here. It's already a 1. So we have a sum of squares with a leading 1. Fine, no issue. So we're going to let x be tangent theta. So that'll be our substitution, tan theta. What's the derivative of tangent? Secant squared. So we're going to have a dx equals secant squared of theta d theta. Now we're ready to convert everything in here. Let's do everything. So the dx becomes a secant squared of theta d theta. And in the bottom, we end up with 1 plus tan squared, all raised to the 3/2 power.
Integration by parts?
Woo! So what is 1 plus tan squared? Visualize that triangle, secant's on the hypotenuse.
Secant squared.
Yep, 1 plus tan squared. You gotta have that triangle in your mind so that you can do it quickly and easily. So that's secant squared. Secant squared to the 3/2. Isn't that just going to be secant cubed? Because in here, all of that becomes secant squared. And power of 2 raised to a power of 3/2 gives us a power of 3. Right? Everyone agree with that? Okay, so then what does this whole integrand turn into? And what's 1 over secant? Cosine. Oh, look, this is a trig sub one that actually is pretty easy. So now with this back substitution, we have to go from thetas back to the original variable, which is x. So here's where we draw the triangle. Draw our cool triangle here. So we're going to draw it in quadrant 1. tangent of theta is opposite over adjacent. And then we fill in the hypotenuse by using the Pythagorean theorem. So we've got that. All we need is sine of theta. So sine of theta is
X over square root x squared plus 1.
also known as 6.
Yeah. See, that's pretty easy to use that.
Is he using a special method?
Yeah.
Theta is always the angle, like the quadrant 1 angle. So think of the rotation of from the positive x-axis. So theta is always going to be that little angle inside. So tangent of theta is x, so opposite over adjacent has to be x. That makes sense?
So did you put the opposite side as an x because that's tangent in the one tangent secant, or because tangent is sine over
So whenever you do your trig sub, you're going to have a ratio here. So I'm thinking if that ratio is x over 1. So I want to build a triangle that will have that ratio as opposite over hypotenuse. So whatever that trig function is, if this was say sine of theta was that, then we would do x there and a 1 there. If it was secant, we would do x there and 1 there.
So are you building this triangle with sine and cosine?
Say again?
So are you building this triangle with sine and cosine, or tangent and secant?
We're building this one with just tangent. The triangle is built with just one trig function. But that one trig function leads to a triangle where you can find sine, cosine, tangent. You can find all the 6 trig functions.
Okay.
But the triangle itself is built from one trig function. Was that a question? Okay, so that's a pretty reasonable one. All right, you all ready to try one on your own?
No.
Weak!
Wait.
All right, well, let's see what the next slide looks like. No, you're ready. You're ready. You're ready. I believe. Okay, so try this one on your own. First step, factor out the 36. So factor out the 36. Remember that 36 is in the denominator, and whatever the power on it is needs to come along with it. It's not a square root. You can do the arithmetic. You can do the arithmetic. Bingo. 36 squared, and is it in the numerator or denominator? When you factor out your 36, is it up top or down below? So it's not a square root though, it's a square, so it'll come out. So instead of 36 to the half, it's going to be a 36 to the 2. Denominator.
Can you just bring out 1 over 36? That doesn't seem right.
1 over 36 squared. We are going to perfect your algebra in this class.
Yeah.
Perfect your algebra. Destroy your arithmetic.
Perfect your algebra, destroy your arithmetic. That should be your first step.
Oh, I forgot he made plate Z.
Is there any Any part of this arithmetic that you want explaining?
Why you keep 36 as, sorry, why you keep 36 squared as 36 squared instead of writing out 1296?
Because I don't know off the top of my head that it's 1296.
Oh, okay.
And what we see with trig sub is there's a lot of division that comes once you integrate, so a lot of times things will cancel anyway, so.
Okay.
Yeah.
Why do they just write z over 6 as z choose 6?
Z choose, wait, what? No. Say that again? Z choose 6.
I put z over 6 in parentheses, and then I forgot to write the fraction bar.
Oh, yeah. So you're trying to pull statistics into here. All right, so there is the step 2. So once we factor out that leading coefficient, we need, maybe I shouldn't call it the leading coefficient. Once we factor out the coefficient that's going to give us the 1, then we need to make sure that we've rewritten it as either a sum or difference of squares, depending on the problem. Here we have a sum of squares. So now it's all teed up for trig sub. Trig sub. And because this is a plus, that tells you you're going to use tangent. So let's see if you can get the next part. So tangent will be z by 6. Tangent z by 6. Z is 6 tan. Derivative here, derivative here. That's good. You're good. On track.
Like, that's the only part I can do. Let's go.
On track. So it's not just z, right? So but we want to write that as a single square first before we do the substitution. So we want it to be a quantity that's squared. We want that to be, like here is not really a sum of squares. Right, so we need to turn this into a sum of squares, so we want to make sure that we rewrite that as z over 6 squared. Then the z over 6 will be what tangent is. So z divided by 6. All right, so everyone get their tangent, the derivative of tangent in there? Where are your angles? Where are your equal signs? That looks like trash.
Well, I like to think it's,
Looks like you're thinking in an octagon.
well, it's kind of the answer. If it hasn't been 10%.
So where are we at? So do you follow the factoring of the 36 out? 36 comes out, it has to come with power. So if it was a square root, it would come out as 6, but it's not.
Why didn't I bring this Tyler to a random trig function?
And then in here we want to rewrite that and make sure.
Oh, this is the DZ.
Power
Yep,
two.
you're right.
We want it to be a square.
But I don't know if this is like
Whatever is below that square, that's going to be what we let.
You let 1 over 60,
Find the derivative
1
of
over
this
6,
side.
z over 6 equals 10. So I think that 6 disappears.
So now we have to substitute back. Substitute back. So this often is a tricky part. So as soon as we do this, we have to remember that the limits need to change. And most of the time with trigonometric substitution, most of the time you just wait till the very end to deal with the limits. So placeholder limits, you can of course do them now if you want, but usually there's better things to do than do your limits early. Okay, so in the numerator, we have a z squared. So from our let statement here, Z is going to be 6 tangent of theta. So Z squared will be 36 tan squared. All right?
With definite integrals, does substitution rules still apply where you don't have to convert it back if you find out the limits for the substitution?
Yes. So you're saying if you found these limits here, we don't have to go back to Z?
Yeah, and you can
That's
solve
true.
like that.
Yeah, the issue is that it can get a little trickier than normal limits because you're doing inverse trig functions. So if you plug in the 6 root 3 here, you get inverse tangent, inverse tan of root 3, which is fine, you can do that. But generally, it feels like it's just easier to do the limits back at the originals. Let's finish up here. So we have, everyone see the 36 tan squared. Z is 6 tan, so we square both sides. dz is 6 times secant squared of theta times d theta. All right, so there's dz. And in the bottom, you have tan squared plus 1 squared. So z over 6 is tangent. So here we have tangent squared plus 1 then. Z over 6. That becomes secant squared. So how many secants do we end up with? A lot, right? Muchos secants. So 36 cancels with the 36, and then a 6 cancels with the 36. So I see a 1/6 out in front.
Are both of those numerators of the same denominator?
Yeah, it's just multiplication there.
Oh, okay.
And then tan squared plus 1, we have heard that that is equal to secant squared. So we end up with secant to the 4th in the denominator. We agree? So then in the numerator, we have a tan squared of theta. We have a secant squared of theta. And in the bottom, we end up with secant to the 4th of theta. So we've got that.
And cancel secant squared.
Cancel out a secant squared. Sounds good. And that gives us tan squared
See, exactly, thank you.
over secant squared. So we've got that. This, once again, is,
Not log.
it's not log form, definitely not log form, and it's also not in the tangent secant power. It doesn't match the powers, right? If we had products of tans and secants, we needed an even power on secant or an odd power on tangent. Doesn't satisfy that. So we're going to go to the Pythagorean theorem, and how do we rewrite tan squared? Thank you, Harrison.
Shouldn't we be leaving placeholders for our bounds?
Yeah, we should have placeholders. Thank you. Okay, and now what do we do? The big S? So we can't quite cancel yet, but once we split them, then it will cancel. So we're going to split, so that's good thinking, right? That's going to cancel once we split. So we're going to do that, and we're going to do that. So we're going to split the fraction. And once we split the fraction, then we can get a nice cancellation. So we're going to have 1/6, split the fraction. That's going to be 1 minus, isn't that cosine squared? All right, 1 over secant squared. So secant squared over secant squared is 1. 1 over secant squared is cosine squared. And 1 minus cosine squared is What's 1 minus cosine squared?
Sine squared.
Sine squared. All right, so we're all the way to there.
Don't tell me you need to power reduce now.
Now we power reduce it. Power reduce it. And when we power reduce it, the 1/2 will factor to the front. And this is going to be 1 minus cosine of 2 theta. All right, so piece of any.
Instead of doing that whole thing, tangent squared over secant squared, that's sine over cosine squared times cosine squared, so you just, secant entirely cancels out, and you don't even need it, you get sine squared immediately.
Yeah, you could also do that.
Yeah.
I mean, if you convert to sines and cosines, then this step here, yeah, you would save 1 step.
Yeah.
Bargain hunter. Wait, what do you mean, Reyes?
U subbing for tangent.
Right here?
Yeah.
No, because derivative, if you take u equals tan, derivative of tan is in the denominator, so that, right? If the secant squared was in the numerator, then yes.
Okay.
Yeah. So at this stage, there's 2 ways you could go. You could turn to sines and cosines, or you could just do what we did, either one. It's not always obvious what the best way is. So if we did switch to sines and cosines, it would save us 1 step. Okay, so now we can integrate. We haven't even integrated yet. Jeez. So sine of 2 theta divided by 2. Placeholder limits. Caitlin,
Do we have to use theta?
what do you want to use?
I don't know.
Why? 6.
You want to use
Like C.
zeta?
I don't know, just.
That's a function.
Theta's dumb. I don't think I've ever heard that before. I've never heard so much.
Everyone in my
Like,
high school hated writing theta, so they use y.
oh, you can use y if you want. What do you want to use?
That would confuse me
Oh.
so much.
No, I was just thinking, because like maybe like a T.
You can use t.
No, I was just wondering if it's okay if I should.
It's totally fine if you, because it's just a dummy variable. It doesn't matter. It's a dumb variable. All this hate for theta.
This equation.
Poor theta.
And rightly justified.
It's the trick. It's getting to me.
It's the trick is
Get to us.
Yeah, it's disturbing you. Okay, so how do we rewrite sine of 2 theta?
See, that's why I was sick of those.
2 sine theta, cos theta.
2 sine theta cosine theta. Very good. Rockin'. I'm going to distribute the 1/12. So we're going to have 1/12 over here. Sine theta cosine theta.
Yes. Hold the book.
Everyone understanding why the 2, why it's 1/12, why there's no like 1/24th? Everyone see that? Because sine of 2 theta is 2 sine theta cosine theta, so those 2's cancel, so that 1/12 comes to both. Okay. Now we use our triangle. So z over 6 is tangent of theta. Let's write that over here. Z over 6 is tangent of theta. So z divided by 6 is tangent theta. So now we get to be creative and build our triangle. Theta is always in this corner. Tangent is opposite over hypotenuse, so we want opposite
That's sine.
over what?
You said it was opposite over hypotenuse. That's sine.
Oh, good point. Thank you. Thank you. I wrote it, I just didn't say it. And then we get that. Yes. Tangent is opposite over adjacent. Opposite over adjacent. So many things to remember. Right? Too many? At least we're only in 2 dimensions.
Oh my word.
Just an observation. So here is where we can solve for theta. Theta will be the inverse tangent of z over 6. So now we can fill in all the blanks. We have 1/12 arctan of z divided by 6. Now, what a crummy letter z is. Jeez.
That's why I use those.
And then 1/12 sine of theta. Do we see what sine of theta is? From our triangle? Z over root. Z divided by the root. And cosine 6 over the root. And then this is a definite integral. We're back to z. Who knows what z was? Let's see, 6 and 6 root 3. All right.
Since these are so long when it comes to an exam, I'm only getting like one problem. Somewhat easy.
There's gonna be, so there'll be at least 2 trig subs. One of them will be definitely as like kind of the quick eat style.
Okay. Like, I understand you didn't learn this, but if I have 6 of these questions up, I can't.
No, there won't be 5 or 6. That's for sure.
How many problems are on the homework?
Like 1,100?
Oh,
6.
Actually,
Questionary?
Is this gonna be math from now on, where it's like not necessarily hard, it's just like there's like a million steps?
Yeah.
Fun.
Yeah. There's no individual step that's hard. It's like Jenga.
Yeah.
Right? Just pulling out one block. Just one
How
block.
is that like Jenga?
What? Your mind is like Jenga, right? You're pulling one little thing out at a time, and all of a sudden it just collapses.
only they're 4-dimensional blocks.
Right?
I mean, yeah, I guess.
It's like Jenga in your head.
I'm missing pieces, I think.
As soon as you see
That's an automatic fail.
oh, the missing link. Here it is. Okay. So let's plug in the 6 root 3 first. Now we have to evaluate our inverse trig functions. So plugging in 6 root 3, we're going to have 1/12 arctan of root 3 minus 1/2. Z is 6 root 3. Divided by the square root. Oh, square root times the square root, they cancel. 6 root 3 squared is 36 times 3 plus 36. We'll multiply that out in a second. So that's what we get when we plug in the 6 root 3. The square root times the square root cancels to just the inside. The inside is z squared plus 36. That squared is 36 times 3. 6 divided by 12 is a half. Now we have to subtract off the antiderivative evaluated at 6. So this is going to be minus 1/12 arctangent of 1. Minus a minus is plus. 1/2. Plugging in 6 now. So 1/2, now we have 6 divided by 36 plus 36. We'll do that in a moment. Arctan of 1/3, which is on one of your note cards. that you read every night before bed. Arctan of 1/3 is, should be instantaneous by now. Arctan of root 3. Pi over 3. Remember that tangent is the same as slope of the terminal ray. Slope of the terminal ray. So when you think about your unit circle, i.e. your third eye, the unit circle should be your third eye by now. This one here at pi over 3 has slope of root 3. This one at pi over 6 has slope of root 3 over 3. So inverse tangent of root 3 is 2 pi over 3. Inverse tangent of root 3 over 3 is pi over 6. Okay, so we're here. So we have the 12 multiplied by pi over 3 minus, that's going to be a 3 root 3 in the top. And in the bottom, we have 36 times 4, which is 144. Minus 1/12. What's arctan of 1? Pi over 4. It's the angle that has a tangent value of 1. The angle with the tangent value of 1 is pi over 4. And then we have 3 over 72. Okay, so let's see. What can we cancel here? You can do the arithmetic here. Let's not think about common denominators right now. That's just too much. That would be the last block. The last block.
Yeah.
Finding common denominators.
Just plug the inverse tangents right into
My
Pearson.
wife that barely passed algebra.
Plug it into Wolfram
Oh,
Alpha.
please do. Oh my god.
I'll show her this on a Halloween scare.
Your mother?
No, my wife barely passed algebra, so I'm gonna
Oh.
show her this problem when I get home and scare her.
Oh, your wife and my wife are friends. That's how I met my wife. Tutoring her algebra. Long ago.
Did the tutoring help?
Yeah, she got an A in algebra.
Oh,
Yeah. But that was 30 years ago. She would not get an A right now. She would not get an A today. In algebra. Nope. She teaches English. Upstairs.
And behold, your 45-minute problem.
Yeah. Oh, that was quick. Okay. Now let's do a secant. A secant. We haven't done a secant yet. This is the one we've been looking forward to. It's the most complicated. No, it's not the most complicated. Okay. So
What is the most complicated?
it depends on the square root. So they all can be complicated. So notice in here that we already have the 1, right? So we don't want to, the factoring that we do is to create the constant 1. Here we don't need to do that. But we do notice that the numerator isn't written as a difference of squares yet. So we want to rewrite that numerator so that it's written as a difference of squares. So we make that 2x quantity squared. And this is usually what you're going to see. They're usually, if they don't write it explicitly, they're thinking x is something that causes no square root of a negative. Here they explicitly told us, so good for them. All right, so we have a difference of squares. Difference of squares is either sine or secant.
Aren't you beginning DX?
Ooh, I forgot I pulled a Harrison. Oh.
Why?
Come on.
Why?
That's, wow, he's rubbing off on me.
Exists.
Yeah, so here is, let's see. Yeah, this is Harrison's DX. Right? Right. Oh! There's his dx, right? Just disappears.
Is domain like an omen for anything?
No, it's an omen for things being easier, so that's not an omen.
Okay.
It's fortuitous. Because it just means that we don't have to worry about anything funny, no square root of a negative. So they're just telling us explicitly. Okay, so we have a difference of squares, and a difference of squares that the trailing one is secant. So we're going to let 2x equal secant of theta. Sine doesn't work because sine squared minus 1 is not an identity. Sine squared minus 1 would be negative cosine squared, and you can't take the square root of negative cosine squared. So only one of them is going to work, sine, secant, or tangent. We take the derivative of both sides. So we're going to get secant times tangent times d theta. All right, now we come back over here and start substituting. So 2x is secant, so in the numerator we have square root of secant squared of theta minus 1. Then we have the dx. So the dx is going to be 1/2. We're going to isolate the dx, so we divide by 2. So we're going to get 1/2, which I'll pull out in front. 1/2. And then secant times tangent. So secant theta, tangent theta. D theta, all divided by x squared. So then we come up here for x. We have to square, so we divide by 2. So x is secant over 2 squared. That's secant squared over 4. So secant squared of theta over 4. We'll pull that 4 out in 1 second. Let's make sure that we're all, maybe I won't use the word happy, but content. That's right. So we're dividing by 4 in the denominator, so pulling out a 4th in the denominator turns into a multiplication of 4, so we end up with a 2 out in front. And then secant squared minus 1, tangent squared. So this is going to be the square root of tangent squared times secant. Oh, no, one of the secants can cancel, right? So we have a secant down in the secant squared in the bottom, 1 in the top, so 1 is going to be left in the bottom. That's secant in the numerator is gone. We have 1 secant left down below. And then d theta.
In the numerator, isn't it just tangent 1/2 theta times tangent theta would be tangent 3/2 theta?
Ooh, say that again?
In the numerator, you have square root tangent squared of theta. Isn't it the same as saying tangent to the power of 1/2? And we're multiplying by tangent theta, so that together they become tangent to the 3/2.
No,
No.
because the square root and the square are just going to cancel.
Oh, duh.
The square root and the square are going to cancel. So we'll end up with tan squared.
We'll end tan squared, okay.
We'll end up with tan squared.
Time for that last G fuel.
It's all happening. So we end up with tan squared. So here's where we have that choice. We could use Pythagorean identity for tan, or we could change the sines and cosines. Now, last time, changing to Pythagorean felt like a really good thing to do because we had a secant squared in the denominator, so we knew that they would cancel at some point. Here, tangent squared, secant squared minus 1, if you think in your mind about replacing that with secant squared minus 1, does it work as easily? Yeah, it will work as easily, right? You're going to get secant squared over secant, which is secant, and you're going to get 1 over secant, which is cosine. So let's go with Pythagorean. You could definitely convert to sines and cosines too.
You have to move this to
It's really whatever, it's your personal preference. How often have you been told that in math class? It's your personal preference. Pythagorean, sine and cosine, whatever floats your boat. Nerdy Newton. All right, any questions on this? So tan squared is secant squared minus 1, hypotenuse minus leg. And then secant, we split the fraction. Let's use this laser. So that thing, we split it. And then we integrate. Integral of secant. Do we remember?
Secant x plus tangent x.
Natural log secant plus tangent, absolute value. Should be thetas. Okay, so 2 times that. And what's the integral of cosine? Sine plus c. All right, we're good, I think. 2 distributed. Now we get to build our creative triangle. So secant is 2x. Theta's right there. What the heck? So secant is hypotenuse over adjacent. We want that to be equal to 2x, so we can think of this as 2x over 1. So we're going to go 2x and 1. And then our missing side over here is the square root, very finicky, this board, square root of 4x squared minus 1. And as you've probably started to notice, when you find your missing side, it usually matches something that's in the original integral. If you get something that looks dramatically different than what was in the original integral, you've probably done something wrong. Spend 20 minutes finding your mistake, and it was on step 1.
Yep.
Why does it say that x is greater than 1/2?
Just so that you're not taking the square root of a negative. Right? If x was 0, you'd have the square root of negative 1. So it's just the natural domain. All right.
Can you show us how to do it if you convert it to sines and cosines?
Sure. So if we switched it to sines and cosines, this would be, so right here, we would have 2 integral. This is going to be sine squared over cosine squared for tangent squared. Cosine will go into the numerator, so it would look like that. That make sense?
Yeah.
So then one of the cosines is going to cancel, and then you've got a sine squared in the numerator with a cosine, so then you're going to have to use the Pythagorean theorem, 1 minus cosine squared, then distribute the cosine squared, and you will get secant minus cosine. So actually, this way is going to be faster in this case. Yeah, but it wouldn't work.
And then we don't have to plug the x factor.
Oh, no, we still have to do that.
Okay.
Yeah, we always have to go back to the original variable. Yeah, always have to go back. So yeah, we got to get back to x. So that's what the triangle is for. Triangle allows us to get back from theta to x. So let's see where we're at then. So going back to x, we have 2 natural log absolute value. Secant is 2x over 1, so that's 2x. Plus tangent is square root of 4x squared minus 1. Minus 2 times sine of theta, opposite over hypotenuse. So square root divided by 2x plus c. So the only thing we can do is cancel out those those 2's. And there is our final answer. Question? You sure? You sure?
Yeah.
If you did these on the test, would you use definite? Or would you use indefinite?
I don't know. I just do maybe one of these.
No.
I want to see if you can do your inverse functions. No more than 2 of those, though. These things are a little long.
Yeah, just a little, just a little.
A little long. It's just feels like brain food, though.
Getting overstuffed at this point.
Botulism.
Early Thanksgiving.
Early Thanksgiving. There we go. I like that attitude. You're welcome. You're so welcome. Okay.
Definitely not
Let's
early
go ahead and
Christmas.
do one more secant. I think we can maybe fit one more in.
If it's definite?
I don't know if we could fit 2 more in. We'll see. You only have 1 left in you?
That was like 3 ago.
So that's the problem with having a 2 hour and 15-minute class. All right, so what is our first step? Favorite F word? Factor. Yeah,
Not
factor.
mine.
So we're going to factor out that 64. That 64 is in the denominator, so it's going to come out in the denominator. And what's it going to come out as? 8, because that square root's attached to it. When it comes out of that denominator, that square root's attached to it, so square root of 64 is 8. And then we have the integrand, we have dx divided by the square root of. There is no 64 with this x squared, so we imagine one. And that 64 right there is the one that came out. So we're left here with x divided by 8, quantity squared, minus 1. Now we have a difference of squares with a 1. That's going to make our trig sub as easy as possible. Should be pretty light. So x divided by 8 is secant of theta. And if you want, you can multiply by the 8. It's kind of doesn't really matter. A lot of times you have a dx isolated, so maybe it's helpful to move it. We take our derivative. So we have that. Okay, now our substitution. Let's see. No errors, no errors. Oh, the numerator is just a dx. That makes it pretty straightforward. So 8 secant theta tangent theta d theta. Denominator, square root of secant squared minus 1. Square root. And what is secant squared minus 1? Tangent squared. And then the square root of tangent squared. They're just going to cancel. You could, yeah, the more, as you start to see these more and more, you could just come right here and say, oh, that whole denominator is going to cancel with that piece of the numerator. Those are just going to cancel out. And the 8's are canceling, for sure. So the 8's cancel. All right, so we are at, let's, So square root of tan squared. And I'll cancel them right here. So square root of tan squared is going to be tangent. Those are going to cancel. And again, technically speaking, the square root of a square is an absolute value, so we would need tangent values that are positive for this to work. And you know, if you looked at all these things here, if you took those limits there, these are all positive. So if you took the inverse secant of those, the inverse secant of positive numbers is positive, so everything is going to work out. We don't really have to think too hard. There's one problem, I think, in the homework where you do have to think hard, but only one problem. Only one. Where you have to think hard about that concept. All right, so let's see. So we're all the way down to the integral of just secant, right? Wow. Integral of secant. And like I said last Thursday, you integrate secant so much from here on out that you cannot help but to have it memorized. So integral of secant is natural log absolute value secant plus tangent. Now we get our chart. But you dropped your tangent. Yeah. But this is tangent squared in the square root. So the square root of tan squared, that's what's going to give us 1 tan. Time for our cool triangle. Our gateway triangle. It's the gateway triangle. It's going to take us from thetas back to x's through the gateway triangle. Secant is x over 8. Secant is hypotenuse over adjacent. Then we need to figure out our missing side, which will be the Pythagorean. So square root of, and it should match something from the original. Like one good thing to notice, if you happen to do this wrong and get 64 minus x squared, that's a good way to check. It should almost always match exactly. Okay, now we're ready to look at that triangle and fill in the missing blanks here. So let's see, we have natural log of absolute value. Secant is x over 8 plus tangent. Is tangent the square root over 8? X squared minus 64. And now we're back to x limits of integration, which are 8 root 2 and 16. So let's go ahead and plug in the 16 first. So 16 divided by 8 is 2 plus, let's see, plugging in 16 there, 16 squared is 256. 256 minus 64 is 192. Yeah. And then we have to take the square root of that. We'll do that in a minute. Minus natural log, plug in 8 root 2, so we're going to have natural log 8 root 2 here is going to give us a root 2. 8 root 2 here, that's going to be 64 times 2, so that's going to be 64 times 2, so that's all, whoa, that's just 1, isn't it? Someone agree with that? 1? Okay, 192. Somebody tell me what 192 is simplified. 64 times what? Times 3, okay. So that's going to be 8 root 3. So 8 root 3, so this is just going to be root 3. Oh yeah, 64 times 3, yeah. 0.80 plus 12. Okay, one more step. We can combine our square roots. We can combine our logs into division. No plus c, we already evaluated. And usually that's where we would stop. Anyone have a question on that one? I've got a great question for you.
Do you expect us to simplify to, if it's like a minus like that, or if it's a plus in multiplication?
It'd be fine if you left it in the log form. Yeah, you won't have to do log simplifications.
Okay.
So, I just added 2 pages. So take a look at this. Tell me what you think. Page color is too bright. Okay, so how about this integral? I am curious if you have inverse of, no, let me just think. Okay, let's suppose we have that. What is the antiderivative there?
Inverse.
Inverse tan, everyone agree? That's arctan? Straight up.
Yeah.
Let's suppose you forgot that was arctan. Which substitution would you make if you forgot that was immediately arctan? What would you do if you tried to do it with trig sub? Say again? Tangent. We would say let x be tangent of theta. And so dx is going to be secant squared of theta d theta. So watch what happens here. So if you forget your basic inverses, you know it doesn't matter because what's going to happen? Let's see. Dx is going to be secant squared of theta d theta. Down to the bottom, you get 1 plus tan squared. What's 1 plus tan squared? Secant squared. So you end up getting secant squared of theta divided by secant squared of theta. So you get the integral of d theta, which is, what's the integral of d theta? Theta plus c. And if you come up here and solve this for theta, theta is inverse tangent of x. So this will get you to inverse tangent of x plus c.
Yeah.
So if you don't recognize a basic inverse, if you just go to trig sub, it's going to come out in the wash. So now you can actually forget about your basic inverses if you wanted. Because you could always use trig sub, just for practice. All right, so take a look at, how did I end up down there? I ended up somewhere very strange. I'll move that. Not sure how I got down there. Okay, so let's stop there. On Thursday, we're going to start PFD, partial fraction decomposition. I read ahead. If you've never done any sort of partial fraction decomposition, then take a look at it because it's simple, but it's got a lot of algebra details in it. But it's easier than trig sub. Trig sub's sort of the hard part in this chapter.
So trig sub is the hardest thing in this chapter?
Yeah. Yeah. I'd say it's the hardest thing in this chapter.
Improper integrals.
Improper integrals are so fun, but they're not as hard. So fun, though. All right, I will see y'all on Thursday.